Hey, this is Dr. B, and let's have a look at electron dot structures. I really like these because they are such a quick and easy way to take a look at the predicted chemical behavior of elements. Do they have limitations? Sure. But are they good for the first couple of rows? You bet. Are they good for the rest of the periodic table? Pretty good. And so let's have a look at them. Here's the electron dot structure for phosphorus. We see P written for the phosphorus atom, and we see 5 little dots arranged like this. What is going on? Well, if you take a look at phosphorus, you realize it has 5 valence electrons. That's 5 dots. All the electrons within the inner shells there are just filled up. So these are the 5 electrons that matter, the ones that are really responsible for chemical behavior. That's the valence electrons. And since we have 8 possible electrons, they want to have 8, but they only have 5, and they tend to pair up. Let's draw them like they go around in a box with 2 per side. So 2, 4, 6, 8, but we only have 5. Somebody's going to have to pair up, and so they draw this. These are known as lone pairs of electrons. They do not contribute to bonding, but we're missing 3 electrons. It will tend to gain those 3 electrons. You may recall that these will tend to form a -3 charge. They can also get 3 electrons by sharing, but that's another topic. They can also perhaps deal with other things like d electron groups, but I really don't want to go into that. The simple model here shows that these tend to form 3 bonds for phosphorus, and that's its electron dot structure. Sometimes you'll see it written as a Lewis structure. It's a quick look at the valence electrons, and let's apply it to neon for something that's even simpler. Find it on your periodic table, and you realize that it's a noble gas with 8 full electrons, so let's show it that way. 2 per side of the box, and this is an example of a stable element. It's not going to do anything. The other elements will try to assume that. In the case of lithium, it's a little bit different because here you only have 3 valence electrons, right? I'm sorry, 1 valence electron, so we just draw 1 dot. Boy, it will tend to lose that one. Beryllium, 2 dots you might draw initially, but we're forgetting about a rule. It's called Hunds Rule. Spread them out. It's better to draw beryllium like that. This also is why we didn't draw phosphorus with 2 pairs and 1 lone electron, because we always apply Hunds Rule. Since there's only 4 positions, somebody had to be paired there. Try it for hydrogen, oxygen, nitrogen, and carbon, and you might see a pattern emerging. Don't forget that we are 95% those 4 elements. They're really fundamental to living things. Okay, hydrogen, you should have drawn 1 valence electron like that. Oxygen, 6, but spread them out, and 2 need to pair up. This is a nice way to try to show them spread out as much as possible. Nitrogen, 5 valence electrons like phosphorus, and carbon, 4 electrons, so we can spread them out like that. Now have a look at the lone campers here, the single electrons. And note that hydrogen tends to form 1 bond, oxygen 2, nitrogen 3, and carbon 4. Honk if you love chemistry. H-O-N-C, 1, 2, 3, 4 bonds. Valence electrons are the key to understanding chemical reactivity, and a very quick way to look at that and to predict the chemical behavior, at least for the first 2 rows, is by electron dot structures.